All right. Well, hi everyone. My name is Özgür Bartuş, and as Ben I mentioned, I'm a member of Format Lab within the Stockman Center for Design Computing. First off, thank you so much for joining me here, both in person and a lot of people on Zoom. I don't even know like what the number is right now, but thank you. 54. Oh, that's plenty. Well, today I'll be presenting my dissertation titled Towards Co-Creativity, Exploring Modalities of Vision-Augmented Robotic Fabrication for Automation and Beyond. This has been a culmination of the past 5 years' work, and I'm excited to share it with you all today. Then I did a really, slides are not advancing. All right. Ben I did a really good job. Ben I did a really good job explaining everyone, so I'm not going to take as much time, but I'd like to very briefly introduce again the committee members, Ben I, Jose, Lucas, Katie, Chris, and Onur. I've had the privilege of conducting my research under the guidance of this amazing collection of minds, who I'm fortunate to have as my committee. All right, I'd like to start my presentation by breaking down the title of my dissertation, which, funny enough, I've been working really hard over the past 5 years to put together. And I'm hoping that this will help establish the critical lens through which my dissertation examines contemporary computer-aided design and fabrication workflows. Digital automation, or in other words, codification of design tasks, has been a significant catalyst in the evolution of contemporary design practices since the early 1960s. But however, despite their advantage and prevalence, these workflows inherently rely on discrete and often abstracted representations of the design context. And this very nature of these computational systems necessitate a conscious effort of defining design problems and discretizing design parameters in computable chunks, which effectively imposes a certain way of engaging with the design context. Not necessarily good or bad, but a certain way. It is typically a different kind of way of interacting with it. This limitation is especially clear in digital fabrication workflows, where we rely on geometric assumptions to represent the environments we operate in and the materials we engage with. However, these assumptions rarely reflect the true state of the material context and present significant limitations, even when we're using the most advanced robotic manipulatiors. Even in an optimal case, where we're using highly engineered materials, well-established fabrication techniques, the materialization quality still remains indeterminate, as the inherent material behavior and the complex tool-material interactions present a wide range of uncertainties. To compound this further, due to the reliance on unidirectional flow of information from ideation to representation and to materialization, these systems cannot facilitate the level of adaptability inherent in how we engage with design and materialization problems through a series of seeing, acting, and seeing. This lack of adaptability to the material context creates major challenges for using these systems beyond simple automation. When the final design is uncertain, or the quality of materialization is unpredictable due to complex material behavior, these systems struggle very much. Such situations might include hands-on exploration of material properties or affordances, or using non-standard materials and fabrication techniques, which inherently conflict with the abstract and rigid nature of computational systems. Within this problem definition, I'm interested in the recently emerging concept of co-creativity within the scope of materialization processes. Drawing from human-computer interaction literature, this paradigm reconsiders computational systems as active agents capable of inferring operational context and appropriately adjusting the computational hypothesis. In simpler terms, my dissertation advocates for computational augmentation of robotic fabrication systems to elevate these systems beyond mere executors of predefined tasks . Okay. I'll take it again. In simpler terms, my dissertation advocates for computational augmentation of robotic fabrication systems to elevate these systems beyond mere executors of predefined tasks into adaptive collaborators capable of sensing and responding to the material context. All right, especially with the recent advancements in sensing technologies, deep learning-based perception models, and heuristically learned action policies, the current technological landscape presents rich grounds for exploring more adaptable and responsive computational systems. However, when it comes to manipulating the physical world, these novel computational approaches are still at an experimental stage, often dealing with what's called toy problems. Therefore, achieving co-creativity in materialization scenarios is a distant but rapidly approaching goal, which guides my exploration of advanced robotic fabrication workflows that can respond to intricacies of the material context. Within the scope of this dissertation, this definition, my dissertation explores how to create computational feedback loops that connect digital representation, robotic materialization, and most importantly, the material context, all overseen by a human agent. To achieve this, my primary focus has been integrating computer vision methodologies into robotic fabrication workflows to facilitate an intrinsic representation of the environment for informed tooling operations. In the coming sections, I'll present my findings on state-of-the-art applications and discuss the development of the computational systems that enable such augmentation. Within the scope of my dissertation work, I delineate three modalities in which vision-based sensing paradigms can augment existing materialization scenarios. The first of these modalities is informing computational systems of the existing material context. Within this scope, I explore how accurately and reliably we can sense the environment, identify key operational parameters and computational strategies for effective deployment, and demonstrate scalability to large-scale applications. The second modality involves adapting tooling operations based on the captured state of the environment and responding to changes in the that's happening within the work cell. This section explores fabrication feasibility for both small and large-scale applications and develops computational strategies necessary for effective materialization. And the last modality focuses on using vision-based sensing to capture the materialized artifacts and assess the quality of materialization. I explore its feasibility in high-precision monitoring tasks and quantifying material behavior in novel fabrication scenarios. Cumulatively, these three modalities mimic the seeing, sense, acting, seeing paradigm in how we engage with the material and design context, aiming to facilitate a more adaptive and iterative digital fabrication workflow. Moreover, this framework structures how the research outcomes will be presented today. Although this is a compilation-style dissertation where each chapter corresponds to a published or under-review paper, these modalities were essential for meaningfully situating my findings. Starting with the state-of-the-art applications employing vision-based sensing, the systematic literature review presented as part of this dissertation adopts a rigorous search keyword framework. This approach has been critical in adequately surveying this emerging field, which currently lacks coherence in terminology. This search resulted in 94 papers dispersed worldwide with a significant concentration of efforts in Central and Northern Europe, as well as North America. Despite the fact that no date limits were set in our search, the selected corpus indicates that this area of focus emerged in the early 2010s, coinciding with the commercial availability of computer vision hardware like Microsoft Kinect, as well as open source efforts that support it. From 2012 onwards, we see a significant increase in research output, with conferences being the most prominent outlet, highlighting the rapid pace of progression in the field. However, there's a significant shift towards more thorough delineation of findings through more extensive journal publications in the past few years. In analyzing this corpus, this literature review presents Vision-Augmented Robotic Fabrication framework, which identifies and delineates implementation and operation considerations critical to effective deployment of these systems. Within this framework, The selected precedents are categorized by their fabrication methods as additive, subtractive, formative, and disassembly, assembly. Similarly, sensing technologies are also grouped based on their sensing principle as laser-based measurements and optical imaging systems. Moving on to operational configurations, this literature review examines how sensing hardware is employed within the robotic work cell. And here, my categorization borrows from the literature in robotics, where these configurations are typically divided into eye-in-hand or eye-to-hand configurations. In addition, I define common computational strategies to accurately register spatial information with respect to a known coordinate frame, such as the robot base. Okay, regarding how the environment is sampled in these precedents, I categorize the identified strategies based on the permitted degrees of freedom between camera poses as shown here. And especially in applications where environment is sampled using more than one camera pose, the integration of these spatial data becomes very critical. Here, this literature review also identifies high-level strategies adopted in the corpus as point cloud accumulation, spatial representations, and sensor fusion algorithms. And lastly, I categorize the modalities in which these robotic fabrication systems operate as deterministic, or we can call it a single cycle, iterative, multi-cycle, continuous, real-time. Through this detailed examination of the state-of-the-art methodologies and strategies, I identified several gaps in knowledge, including inadequate discussion of computational systems and strategies, limited systematic investigation into operational parameters, scarcity of quantitative assessment of perception accuracy, lack of open source implementation for better replicability. And these findings inform the development of vision-based sensing framework presented in this dissertation. And as part of this development stage, I've developed and prototyped a hardware assembly, which includes NVIDIA Jetson Edge computing device and Microsoft Azure Connect developer kit. This allowed us to interface with the robot using Jetson's digital pins to ensure synchronized acquisition of data at precise camera poses. Here you can see, well, not yet, but here you can see an example run with the camera assembly. At the bottom, you can see the digital signals in real time and the state of the scanning procedure. In this example, digital output 0 triggers the start and end of a scanning procedure, where digital output 1 is used to capture an individual frame at a known position. And the other major leg of this development process was the scene reconstruction algorithm. For this challenge, I opted for a voxel-based integration algorithm developed by my collaborator Wei Dong as part of his PhD dissertation. And this approach was critical in the success of this development phase, as it utilizes hardware acceleration for efficient integration of multi-view spatial data, as exemplified here. However, this integration algorithm alone is not quite enough to produce operable geometries needed for toolpath generation and so on. Here you can see some of the artifacts. Now you can see it. Here you can see some of the artifacts caused by sensor noise and imprecision in sensor pose estimation during the integration process. Luckily, this is a well-studied problem in the field of computer graphics, and by using an outlier removal algorithm, there we go, I was able to achieve clean geometries. And if we were to look closely at this mesh, we can see that the details are very well preserved, successfully capturing the overall geometry. This particular output is reconstructed using voxel size of 2 millimeters and consists of more than 8 million polygons for the whole scene. And for those of you who do not really deal with mesh geometries on a regular basis, that's a lot of faces. Luckily, this spatial hashing approach allows for tuning of reconstruction resolution to match the accuracy needs of specific context. As we can change the voxel sizes, the flexibility presents significant advantages both in terms of computational efficiency and scalability at large. And this successful implementation of hardware and software components marked the first major milestone of my dissertation research, setting the stage for extensive exploration of its capabilities. And following this development stage, this vision-based sensing framework was validated across different material systems and fabrication scales. From left to right, the first journal publication included in this dissertation investigates the accuracy of digital twin reconstructions and fabrication feasibility of informed tooling operations in small scale. Next conference proceedings explores the use of reconfigurable and reusable SEN formworks enabled by vision feedback through a proof of concept case study. The third conference proceeding integrates the vision-based sensing to quantify post-fabrication deformation of mycelium-based biocomposites as part of an internal collaboration at Format Lab. And lastly, as part of the collaboration with the AdCon lab at Penn State, large-scale validation study on the right explores operational scalability to large-scale 3D printing concrete applications. Within the scope of this first modality identified as part of my dissertation, my goal was to assess the reconstruction accuracy and reliability, as well as to identify operational parameters and develop computational strategies. And the research questions guiding this investigations are how accurately can we sense and digitally reconstruct the work environment? How do operational variables impact the accuracy and reliability? How effectively these strategies can be scaled to large-scale applications. And to methodically assess the validity of the system that I developed, I developed also an experimental methodology comparing robotically fabricated surfaces against both the scanned mesh as well as the original NURB surface. Here, the goal is to infer both the accuracy of robotic materialization and respective digital reconstructions, effectively investigating whether vision-based sensing feedback can match or beat our assumptions about the material context. Using a hot wire cutter, we first fabricated surface geometries out of a 60 centimeters by 60 centimeters EPS foam block as shown here. These surfaces were then probed with a contact-based measurement approach using a digital dial indicator with an accuracy of 0.01 millimeters, densely sampling the surface roughly every 15 millimeters along cardinal axes. All the target points were programmed to probe 10 millimeters deep to allow for measuring sign error within the measurement range of the digital dial indicator. And if we take a closer look at an individual robot target, we can see that the discrepancy between the known offset amount and the measurements taken from the dial probe gives us the error between the digital master and the physical surface. And by projecting these points along the surface normal vector, we can also calculate the error between the reconstructed mesh and the physical surface as well. Using this methodology, we investigated two operational and computational parameters, namely the effect of camera pose count and voxel sizes in reconstruction quality. To systematically explore camera pose density, we have adopted a hemispherical scan trajectory with ample distance between the scanned surface and the camera to avoid any clipping of spatial information due to hardware intrinsic limitations. This hemispherical scan trajectory was defined by angles scanned in YZ and XZ planes to 60 and 90 degrees respectively for robot posability, with camera pose densities ranging from sparse 2x2 capture all the way up to 16 by 16 captures. And as for the reconstruction resolution, we describe the unit voxel size as the number of divisions per unit length. Here, a single voxel represents the smallest computable unit in which we operate. And there is also my cat voxel, which is like the silliest and tiniest unit in my life, but that's a whole topic for another presentation. Coming back to today's topic, we define a single voxel size as x over 512 meters. And in our experiments, we use x values of 1, 2, and 3 meters, which corresponds to roughly 1.9, 2.9, and 3.9 millimeter resolution accuracy, respectively. Here you can see the visualization of a reconstructed mesh colored by distance to the probed points. With this color mapping, the color yellow indicates no deviation, and the color blue and red represents deviation in positive and negative directions along the surface normal, respectively. Here we see that as the number of poses gets larger, we achieve much closer results to the physical surface, as we would expect. However, beyond the 8x8 pose configuration, at least in the scale that we were working at, we observed diminishing returns in accuracy gains. From these results, we can infer that the reconstructed meshes provide as good or better results when compared to the assumptions that the physical surface is true to its digital master. And building upon this solid foundation, our collaboration with Adcon Lab at Penn State explored how vision-based sensing systems operate in large-scale 3D printing concrete applications in an emulated, still in a controlled environment, emulated site conditions using sand and gravel print surfaces. This shift in scale is challenging, not only due to the increase in the volume of spatial data, but also because the sheer scale of the application necessitates careful consideration of how the material context is captured. To systematically explore environment sensing strategies, I structured this investigation based on the permitted degrees of freedom between distinct camera poses, developing 5 sampling strategies as presented here, tailored for 3D concrete printing applications. Here, the fixed strategy mimics a static placement of the sensing hardware looking top-down to cover the entire aggregate bed at once. The sweep strategy utilizes pure translation motion between poses and isolates the rotational accuracy of the robotic arm. The inside-out strategy primarily relies on rotation around a single point to capture robotic work cell with minimal kinematic reconfigurations. And the outside-in strategy utilizes a hemispherical trajectory, sampling the aggregate bed, looking at 4 points along the major axis of the aggregate bed, aiming to maximize pose variability. Lastly, the adaptive strategy uses a coarser reconstruction of the aggregate bed to optimally place the sensing hardware in terms of distance and angle to the scanned surface. Both the sand and gravel print surfaces were scanned across these different strategies, as well as different camera field of view configurations. And using a contact-based validation approach similar to the preceding work, both surfaces were probed to assess reconstruction accuracy sampled from each respective digital reconstruction. Here we sample a 1 meter by 2 meters region within the reconstructed digital twin of the aggregate bed, defined by the maximum reach of the larger robot that we tested this configuration with at Saito. Another here is coming. Okay, here you can see the resulting geometric reconstructions colored based on assigned deviations from the contact-based ground truth. The top and bottom row, top 2 rows are for the sand surfaces, and the bottom 2 rows are for the gravel print surfaces, representing surfaces that we commonly encounter in situ concrete 3D printing scenarios. But beyond the geometric complexity of these arbitrarily shaped print surfaces, the difference in the aggregate size also poses significant challenges in accurately inferring depth, also due to the limitations in sensing hardware as well. Within this visualization, green indicates little to no deviation between the physical surface and the digital twin, and colors red and blue indicate deviations in positive and negative directions, respectively. Here we can observe that the resulting accuracy using the wide field of view configurations is significantly impacted by the unaccounted lens distortion, despite its inherent advantage of capturing a larger region in a single exposure cycle. In narrow field of view reconstructions, we observe that both the adaptive and sweep strategies perform the best. The fixed strategy exhibits visible distortions of the spatial data. The inside-out strategy results in a significant localization of errors directly below where the camera is positioned, which we can tentatively link to a combined effect of suboptimal angle of incidence, as well as lens distortion that is prominent around the edges of the images. And lastly, the outside-in approach presents compelling accuracy results along the major sampling axis, but this accuracy rapidly declines as we move away from the central region. And in addition to sensing strategies, we also tested computational and operational scalability of this framework by systematically reducing the reconstruction resolution and the number of poses. Similar to our previous findings, we observed comparable results despite the reduced computational complexity of the digital twin representation. Even at the quarter the pose density and third the resolution shown on the top right, the result is fairly comparable to the original data sets on the bottom left, which uses 128 poses and 1.9 millimeters voxel size. And going back to the research questions guiding this exploration, I can safely say that the contact-based validation methodology presented here provides a robust baseline to assess digital twin reconstructions. Material, computational, and operational parameters are critically important in adequately sensing the material context and require thoughtful consideration. And lastly, the presented framework is well capable of operating in large-scale applications with high computational efficiency. However, this transition necessitates additional computational strategies to address scale-related complications. Moving on to adapting. As part of this second modality explored within this dissertation, I explored how the inferred geometric information can be used to inform robotic fabrication tasks and conform tooling operations to existing conditions. Here, my investigations were guided by, one, how feasible is vision-informed conformal tooling on unknown surfaces? Two, what kind of opportunities do such advanced tooling capability hold? And three, is this conformal tooling strategy feasible in large-scale applications? As part of the small-scale validation study, we have explored various tooling operations, including pen plotting, hot knife carving, and 3D printing clay as an early investigation into this capability. And using these end-of-arm tools, there we go, we ran simple tool paths across the surface, shown here as an early investigation of how feasible fabrication is with using this tool path approach. Although we observed minor deviations in 3D printed layer heights and plunge depths for carving tasks, these deviations were actually consistent with the regions that exhibited lower reconstruction accuracy anyways. However, to add another layer of complexity, we, meaning me, Benai, Paniz, we all got our hands dirty, created an arbitrarily shaped surface just to actually test the system on a more challenging topology. And this surface was then scanned to inform conformal material deposition using a differential growth curve algorithm. In line with other tooling tests on known surfaces, this was also a major success where we were able to 3D print on the unknown surface geometry with high precision. Here, you can see the final printed artifact, and during the printing process, we observed consistent material deposition with no visible over or under extrusion across the entire print trajectory, even at 4 millimeters layer height that we were operating in. And finding out this capability, this newly found capability, to further explore this newly introduced capability of conformal material deposition on digitally unknown surfaces, we conducted a follow-up study that investigates how vision-augmented robotic fabrication workflows enable adoption of reconfigurable and reusable sand formworks. Here, the robot is used to parametrically manipulate the reconfigurable sand formwork, capture the resulting material expression, and use this geometric information to adapt tooling operations. As part of this case study, we adopted a very simple modular wall section design as a proof of concept, informed by the constraints in available extruder and the kilns and ceramic firing kilns. Out of these panels, we selected one characterized by a wide range of plunge depths as shown here. And together with our collaborator, Emily Eisman from School of Visual Arts at Penn State, we developed a special sand mixture that holds its shape when compacted, but it can be fired in the ceramic kiln safely to provide support during the firing process, both transport and firing process, and can be reclaimed afterwards. here you can see well, you just saw the formative shaping of the sand mixture by the robotic arm. However, this formative process exhibits varying levels of materialization uncertainties. For example, sand springs back when pushed and making it difficult to anticipate the resulting geometry, which necessitates a more active approach to capture the state of the formwork, in which we utilize the vision-based sensing to geometrically reconstruct the formwork. This geometric reconstruction was then used in generating conformal toolpaths. And to facilitate effective material deposition, we refine our toolpath generation approach using differential growth curves to allow for more precise control over the geodesic spacing of the laid material filaments. And additionally, we incorporated a very simple post-correction approach to ensure smooth and collision-free execution, especially around the regions of high curvatures as shown here. And by combining all these computational and operational strategies, we were able to successfully carry out effective materialization of plate panels on reconfigurable and reusable formworks. Here, you can see all the stages involved in this novel materialization scenario, including the generation of robot targets to parametrically shape the formwork, top left, geometric reconstruction of the resultant formwork geometry, conformal toolpath generation, as well as the printed panel before and after the formwork is removed following the firing process. And in addition to these small-scale explorations, the conformal tooling capabilities were also tested in large-scale 3D concrete printing scenarios as well. In such in-situ applications, site conditions are almost never optimal, and the ability to conform material deposition presents a promising opportunity to enhance the applicability of such technologies at large. And together with collaborators from the ADCON lab, we were able to successfully execute conformal material deposition on arbitrarily shaped sand and gravel print surfaces using a simple meandering path. And during the printing process, we did not observe any significant problems aside from oscillations induced by rapid changes in movement speed and direction, and the extruded material closely conformed to the printed print surfaces. Additionally, these extruded material filaments were also measured by hand using a caliper to assess the quality of conformal toolpath generation, using a very naive assumption that material deposition rate is constant and the layer height and width are inversely proportional. When we distributed the materialization errors along the toolpath, we observed consistent material deposition aside from some localized errors, especially on the farther side. However, we think that this can be tentatively linked to some errors that we observed in the positional and rotational accuracy of the robotic arm that we were using for these experiments. And overall, these results demonstrate that informed tooling of unknown surfaces is well within the capabilities of such vision-augmented robotic fabrication workflows. And moreover, we exemplify that this capability opens up novel opportunities in materialization, such as using reconfigurable aggregate-based formworks or tooling on found materials. Despite the added challenges of large-scale materialization, like I mentioned just earlier, we successfully apply these strategies in 3D concrete printing applications as well. The last vision-augmented robotic fabrication modality explored as part of my dissertation aims to investigate the potential of vision-based sensing systems in monitoring tasks. The underlying research questions for this phase of my inquiry are: one, can we infer materialization accuracy from reconstructed digital twins? Can we actually trust this information? Two, how can we identify systematic errors inherent in materialization process? And question three, can we use digital twins to monitor material behavior of novel material systems? As part of the validation efforts in large-scale 3D concrete printing applications, we explored the precision at which we can infer the materialization quality of the conformally printed meandering filaments. In addition to these conformal first layer deposition scenarios, we also 3D printed a multi-layer wall section, of which we captured the top layer for a similar analysis. Using previously known toolpaths as the ground truth, we explored how effectively the reconstructed digital twin can capture the deposited material. In the conformal first layer deposition scenario, however, we observed significant loss of geometric fidelity due to the lack of depth contrast between the laid material and the background print surface. On the top left, you can see that the regions where the extruded filaments meets the surface is significantly smoothed over due to accumulation of such errors across different poses. Although the multi-layer scenario provided a cleaner signal overall, we observed still a significant variability in our geometric decomposition results, especially around the regions where the filaments start overlapping. And across both first layer experiments as well as the multi-layer scenario, we observed limited agreement between the caliper measurements and geometric decomposition results, which suggests that we still have a little bit more work to do. In addition to the intra-layer material deposition quality, we also employed the vision-based sensing framework in capturing the 3D printed concrete wall section as a whole to assess global geometric fidelity. Using the known toolpaths again as the ground truth, we were able to calculate how materialization errors localize across this multi-layer structure. And as part of this investigation, we first explored the visualization of this data set centered around the total mean. And here, the gradual change in color toward the bottom signifies inherent systematic errors in capture and reconstruction of the wall section. However, by centering the color mapping around the mean deviation of each layer, assuming that the errors on each layer are equally affected by these systematic errors, we were able to isolate the effect of these systematic problems. Here we can identify a number of errors in materialization accuracy, including one, the loss of geometric fidelity around the regions of quick direction change, such as like the corners, as well as the loss of geometric fidelity on high frequency features, such as the one that's shown on the southeast view, where you see a bunch of reds and blues that kind of emerge along the little perturbations. In addition to high precision monitoring tasks explored in 3D concrete printing, the vision-based reconstruction was also integrated in post-fabrication monitoring of mycelium-based acoustic panels as part of an internal collaboration within the Format Lab. Here, the anisotropic nature of this novel material system presents significant challenges, as such composite materials exhibit significant deformations post-fabrication. And by scanning and reconstructing digital twins at distinct post-fabrication stages, as shown here, we were able to quantify both materialization error as illustrated by the 1-2 pair, as well as the cumulative deformation as presented in the 1-5 pair. And through this investigation into monitoring capabilities of vision-augmented robotic fabrication systems, we demonstrated the feasibility of assessing materialization quality and identifying systematic errors. Although we encountered some systematic errors in large-scale experiments, overall, the results present promising leads into how computational systems can effectively capture the impact of their actions in the physical environment. In conclusion, by investigating these different modalities of vision-augmented robotic fabrication, my dissertation documents the integration of advanced computer vision approaches to inform computational systems of the physical environment. It effectively demonstrates advanced tooling capabilities enabled by vision-based sensing paradigms and explores its immediate applications in small and large-scale materialization scenarios. Within this broader ambition of this dissertation to advance digital fabrication systems into a collaborative partner, The work presented here lays the groundwork for adequately sensing and appropriately responding to the material context explored through a series of automation tasks. And in this journey towards co-creativity, closing this first link between the digital and the physical enables a shift towards a computational seeing, acting, seeing paradigm, mimicking how we designers engage with the material and design problems. Although I still believe this goal is a distant one, necessitating computational capabilities beyond what can be feasibly achieved today, this dissertation exemplifies how such incremental advances towards this goal can have immediate impacts in augmenting existing scenarios. And within the scope of this dissertation, some of the key findings are that, one, vision-based sensing frameworks need careful coordination and orchestration of many systems and parameters to work optimally. Two, sensing strategies are key for making these systems accurate and feasible, and they play an important role in how well we can capture the reality. Vision-Augmented Robotic Fabrication presents extended materialization abilities by sensing the material context. And these systems, however, these systems work best right now, at least in controlled work environments. Digital twins, we also demonstrated that digital twins that can help monitor systematic materialization errors and uncertain post-fabrication material behavior. As part of my dissertation, some of the most prominent contributions are, one, the extensive review of vision-based sensing feedback loop in architecture robotic fabrication, which actually got accepted just yesterday, literally. Development, documentation, open source sharing of vision-based sensing hardware prototype to enhance replicability and sharing practices across the field. Thorough evaluation of operational accuracy and fabrication feasibility in both small and large-scale applications. Identification of critical operational variables in adequately sensing the environment, and delineation of computational and operational strategies to support such advanced tooling tasks. However, as with anything good, this dissertation also has some limitations. For example, the generalizability of the results across different material systems and operational conditions is a significant hurdle in adoption at large. The vision-based sensing framework is fairly sensitive to errors in calibration and execution of different computational components, and the need for custom sensing and data interpretation approaches tailored for different fabrication scenarios complicate the applicability of computational and operational strategies across different implementations. And within the scope of future work enabled by this dissertation, the integration of real-time applications is pivotal. Such integration can significantly enhance the adaptability of robotic fabrication workflows by enabling workflows. By enabling robots to respond dynamically to changes in their environment, we can achieve a more dialogic interaction between the robotic systems and the materials that they manipulate. This adaptive capability is essential for addressing unique challenges presented by different fabrication scenarios, leading to a more precise and open-ended process. Furthermore, exploring reinforcement learning paradigms offer promising avenues for exploration. These paradigms allow robotic systems to learn heuristically through interaction with the world, and by continuously adapting to feedback, reinforcement learning can help develop novel materialization techniques that are in constant conversation with the material affordances. This means that robots could better understand and predict how materials behave intrinsically, leading to a more refined and effective fabrication methodologies. And lastly, recent advancements in 3D generative models could offer novel capabilities for generating design hypotheses based on the current state of the materialized artifact. This enables a more open-ended exploration through direct engagement with the material, fostering novel design fabrication paradigms. Before I conclude my presentation, however, I would like to extend my heartfelt gratitude to a long list of individuals whose support has been invaluable through my journey. But to make this more engaging, I'll leave you with a clip of one of my experiments running in the background to hold your attention just a tiny bit longer. Well, I'll start with my comedy. Benai, I don't know. There are a lot of things to say, but not enough words to actually say it all. Yeah, it's been like 12 years, and I'm really happy that we did this all together. Lucas, thank you so much for agreeing to take on this, even as you were just like stepping out the door. And thank you so much for taking time to be here and not be in the beautiful Aegean coast. Jose, thank you for all the opportunities that you provided within SCDC through collaborations, through teaching opportunities. I really appreciate all these little things that make me a bit better scholar. I hope. Katie, I hope I was able to do justice to the 10,000 feet views, and I really appreciate you making me pull back up to that level and look at my work again and again. Chris, finally, I'm really happy to have met you in person, but I really appreciate all the critical questions that comes right at the end of all my committee meetings and always sparks something in my mind. And Onur, for always being there to remind me why I do what I do, and always try to nudge me in all these amazingly mind-opening areas. In addition to all these beautiful people, there are a few others that are not here necessarily, but who made a significant impact in my journey getting to this point. Daniel Cardoso and Joshua Bard, they were incredibly instrumental in helping me conceptualize all of this. And Mina Özkar, Şebnem Yolnay, they've been like, their support has been very critical from the get-go. Format Lab members, old and new, Elena, Ali, Pooja, Natalie, Alale, Maniz, Kiran, Kali, Kiara. I'm proud to be your peer. I really enjoyed working with you guys all, and really appreciate all the fun times we had, and all the little chats we had here and there to kind of like get our heads off the work. Our collaborators, Wei Dong, Emily Eisman, Alireza Zamani, thank you so much. You made this just a tad bit easier, and that's all I needed to get through. AdCon Lab, especially in the last sprint, they were really helpful. Gonzalo, Ali, Nusrat, Amir, I'm sure I'm missing a whole bunch of names as well, but thank you all. People at Autodesk, Erin Bradner and Sachin Chitta first. Thank you for believing in my vision and for your support in my research. Adam, Yodo, Wei, Nick Carey, Nikot, Sri, Carl, Gabby, Noah, Michael, and all the other people that I'm 100% sure I'm missing some. Thank you all for expanding my perspective and make me love what we do even more. And amazing people whom I'm lucky to call my peers. Gamze, Koray, Idil, Jimmo, Weiwei, Ardavan, Emek. They're all around the world somewhere, and I really appreciate. Well, if you're on Zoom, love it, but if you're not, it's fine. I understand. Life is life. And friends all over the world. Onur, Khan, Atalay, Yital, Jem, Cici, Ford. I don't know. I think I'm still missing some, but forgive me for that. Thank you so much. I always needed one of those moments where I am not a graduate student as much and can really enjoy just the moment itself. People of SCDC, Alden New, Julio, Vina, Farzana, Dima, Hanin, Chaudhry, thank you all for lovely chats between work. Marissa, I'm honored to have walked this path with you, and Paula and Steve. I thank you for being my American family throughout this process. My cousin Moot, who really pulled through for me in this last sprint, and my larger family, my grandparents, aunties, cousins. I hope I can make you proud. And lastly, mom and dad, and especially mom. thank you for all the goodies today. But yeah, well, that's a thank you.
Okay. So I would like to open I would like to ask you, sorry, I got a little bit emotional with that emotional talk. It was good.
Hey,
Okay.
you started first.
I'd like to open the floor to the audience here in person first, but people on Zoom can also type their questions, or if you raise your hand, I can also pull you to among the panelists, so you can ask your question in person. So, but I'll start with the people in person. Do we have any questions from the audience? Yes.
Did you cure and save any of the clay tiles as a memento?
There's one. There's one. Yeah, the ones that got fired, perfectly well preserved. But the rest, they kind of get crumbled away anyways. But I have one.
Somewhat complicated question, but I'll try to boil it down.
All right.
I assume that you used some existing image processing routines to do the construction, the digital construction of the surface from
Correct.
camera views.
Cool.
Yeah. Okay. So if we're trying to assess surface quality, not sort of gross conformance to a preconceived shape, but say local porosity.
Okay.
You mentioned in connection with the gravel bed that you had some problems, I think you said, due to maybe depth of field, possibly due to insufficient contrast between the printed material and the background.
Yeah.
So the question is, finally, did you consider alternative modes of lighting the scene?
Yeah, that's
raking light, for example, or multicolored light from different directions.
So the funny thing is that the most ideal situation, at least for depth sensing using the device that I use, which actually uses an infrared range projection, is no light at all. So it's a funny conundrum where like it's us human beings, we do want more light, but machines don't necessarily want that much light. They want it to be controlled, and they want to see only the light that they project into the world. Have I considered like lighting or other approaches? Yes, absolutely. However, one of the things that I wanted to achieve through my dissertation was to make sure that what I do here is attainable and can be replicated by other people. Because I really do believe that it's a big issue at large for the field that I'm trying to be a part of, where a lot of research goes into building these systems, using these geometric reconstructions. However, like very little gets mentioned, and you cannot really even replicate it. And the reason why I stuck with this machine or this system essentially is that it's like when we started with Benai, we kind of had like a ballpark of $1,000 for like a good amount of money that a researcher can like throw away, quote unquote. And that's the goal that we were trying to meet here. But essentially, I think the entire thing costs like around $700 to $800 with some 3D printing here and there. And yeah, the reason for why I still haven't explored additional ones is because of that. But 100% within the realm of possibilities to be including even together, like it doesn't even have to be separate. It can be both different sensors, some using visible light spectrums, some using infrared spectrums, maybe some of them using lasers or whatnot. And yeah, that is something that I personally do want to pursue in the future, looking into this idea of multi-scale and multimodal scanning and understanding the world. Just like you said, maybe not the gross thing, but if need be, can scale all the way down and can work on like a much smaller subset of the geometric world that we live in.
So in this case, the light used for sensing was primarily that projected by
Correct.
the camera itself, not the ambient light.
No, not the ambient light. I have explored a little bit of like just using RGB images, just essentially like how we take images with our phones. But the problem here was problem there is that those kind of techniques mostly rely on having some kind of features, some visible features, be it a pattern, be it like little speckles, and not a lot of the applications that we work with, they don't necessarily have as good of a feature set, like we're working with sand. It does have some kind of a, it definitely does have some, but it can very easily get mixed up with another part of the sand bed that we were scanning, and can complicate a lot of these issues. But yeah, it is within the realm of possibilities, and I do personally want to explore that route as well, especially with the more like recent advancements using neural representations and whatnot.
Thank you. Congratulations on the work.
Appreciate it.
I don't have a question, but I have a kind of humble feedback on otherwise beautiful, really outstanding presentation. Thank you for that. You had a long list of things at the end, but I think you forgot one person. No, like that orange brand fencing.
I know. I also forgot you as well. Hakan, thank you. Both you and the robot. Yes, no, absolutely, absolutely.
I like the robot.
Well, yeah, to be honest, like when I first started here, when we're talking what my research could be with Benai, she was just getting into mycelium research. I was like the second year or something of her exploration. And I decided that I want a good buddy that will always do what I say to do, and will always be there for me. But yeah, this one especially, the one downstairs, big hug, love. Yes,
So 3 rapid fire questions.
Okay.
And a longer question.
shoot.
Chris, can I say something?
Yeah.
We'll have the committee member questions later after the audience. Is that okay?
Yeah, absolutely.
Okay,
All right.
okay. Marcus.
Marcus, yeah.
Thank you so much for the great presentation and for all of the work that went into the presentation in terms of your graphics and explanation. I don't know if this makes sense, but I see the word automation in the title.
Yes.
And I wonder if there are specific goals in terms of how what you're working on displaces human activity. I see so much work. You know, like I wish there was a kind of workflow diagram that included not just the activity of the robot with its end effectors and its sensors, but also the man hours or human hours that are in coding, recoding,
Oh, that's a lot of hours.
and kind of strategizing, I guess, is
Yeah.
the general thing.
Yeah.
So I would like if you could just talk about this word automation, the displacement of activities that are left to humans, and what this machine is doing that makes this somehow more optimal.
Great question. Let me see. Well, I'll start with the point that, like, yes, the idea of automation, and this is also like one of my critique of the field, when every time I look into it, have a perspective on it, is that it used to be this idea of robot does everything. And what I want to do actually is not only just make these collaborators like essentially take more part in what we do, a little bit more at least, but what I want to do is I want them as collaborators. Like I don't necessarily want, like I don't necessarily see, at least in the near future, any capability that can resemble the level of human autonomy in the world, trying to like assess things. Because you're right, it's a lot of human hours. I'll tell you that, like, it's a lot of human hours just getting like something working. Even when something is working on that one machine, making it work on the other machine is also another like whole set of man hours. So in that sense, what I want to do, or like what my work aims to do is, well, one, really do like acknowledge that there is a human oversight. There is no way that we can just let them do what they do, because they just started seeing technically, right? Like they don't even have any understanding of what any of their actions. I actually usually start a lot of my presentations with saying that robots are dumb. They just do what we tell them to do. Like it's a kind of like a love and hate relationship with computational systems for me. Like I love that they do that, right? Because then it's predictable. I can go back and debug it and like figure it out. But at the same time, they actually still do what we tell them to do. So in that sense, it's I would say the automation that I envision within this modality is not necessarily one where you press a button and you just leave. I think there is a lot of things that a human agent can contribute to, especially in materialization scenario, because we're nimble, we're like agile, we feel things way better than like any sensor can, even just with like our fingertips. But instead, to kind of position them so that maybe we use the precision of robots, but figure out a way to actually make them like show us possibilities, like give us some design hypotheses eventually. Maybe they just take an action on what you've been working on and saying like a good friend, you know, you're working late hours in the design studio, someone comes in and says like, oh man, did you mean to put it there? And then you take it out and like everything is solved, that kind of thing. Like that's the kind of collaborator I want. Not necessarily a one that is like, hold on, like take the wheel kind of, you know, no. I want them to be, it's more dialogic. We talk, we engage, we express intents through materials, through other kind of means, but eventually we coexist and we instead of delegating everything to one, we use what each and every one of us can do a little bit, can do best.
Do you think that that type of relationship is unique to the robot?
No, definitely not. For me, like, when I see it, to be honest, in my eyes, a CNC machine is no different than a robot. Well, technically, they're all computer numeric controlled, right? So in that sense, like a robotic system or any of those, any kind of like a desktop 3D printer is the same thing with less capabilities than this robot for me. And it's not unique to just robots. It's not just unique to any of these, but I think it's essentially unique. It's the tension between us as analog beings and them, not them, but like those systems being a discrete system. And then we always have to figure out how we define the problem, how we engage the problem, like with like conscious effort. And what I want to do is make it so that they can help us in that translation as well. They can understand our context, not necessarily just like the little cube that we draw to represent like a brick, where the brick is not even like a perfect rectangular prism. Absolutely.
Yeah.
Thank you so much for the wonderful presentation. I have a quick question and a wonder. So when you talked about the concrete printing, only
Yes.
one filament on the gravel bed, I guess.
Yeah.
And there is a scan of the bed, and we indicated the precision of how well it's scanned there.
Mhm.
And then also a scan of the filament, and you also indicated how well that matched the A, if I remember correctly.
Okay, yeah.
So is there any correlation between how good the scanning is, how precise the scanning is of the bed, and how precise the printing is compared to the A?
I would say,
Can you also repeat the question for the, like, Zoom audience,
Okay,
because they might not hear well. I should have said that to the others.
oh, yeah, well, or show your asked, essentially, correct me, please correct me if I'm wrong, but essentially, is there a correlation between how well we materialize and how well we can capture what we materialize?
Materialization meaning.
Like fabrication, like printing process, so like how precise?
That's in the accuracy of the results. Yes, so if you're creating the digital twin of if the precision of the digital twin of
Yes.
the surface correlates with the precision of the print to the aid print, I guess. So the materialization is then and materialization, I guess.
Like how do errors in the surface propagate into the
Yes.
printed?
Thank you.
Okay, okay, that's a really good question. Well, so far, we've only, to be honest, we only conducted all these fabrication operations with surfaces that we know to be fairly highly accurate. So I haven't tested necessarily how these geometries, like how the materialization quality would end up being if the process was super off. But I would assume that even before we get to materialization problem, there would probably be a lot bigger issues such as collision with the environment, collision with whatever we're printing on, or maybe we'd like try to like print on like mid-air or kind of stuff like that. Essentially, it's kind of like, it's the same thing as like how well you can represent a block of wood in the world for CNC modeling, so that like you effectively use as much of that as much of that process as possible.
So my other question is then probably meaningful. So would it be useful to use the precision of how you capture the surface as an information of designing the path of laying the
So, okay, I see. So essentially, it's a really good question. But the thing is that we assess the accuracy of these tools. We're essentially doing the probing. But the idea is that we hopefully would never do probing, that we can get to a point of just knowing that it's just accurate, or that we have a well-calibrated system that's capable of generating accurate digital twins.
I don't see that it means that, but there are some tendencies, right? So in capturing the precisions, there are tendencies where there are typically areas which does not capture as well.
Yeah.
So my question was, so maybe you can use that knowledge of those tendencies to optimize.
But what I'm saying is, like
You want to mirror.
we don't necessarily know when we're scanning to print how well we scanned. We can only like take a screen, like a snapshot of it, if we were to go back and actually touch it with the robot to know how well we acted. So essentially, I mean, it is possible. I mean, it is possible, but then it's just, then if we're doing, then I think the question becomes, if we're doing a contact-based measurement of the entire surface, why do we even need a vision-based system? Because it's always going to be much more accurate.
Maybe one last question, if we have any from the audience, not from each other. I'll ask the Zoom audience to, I don't see any questions on the Q&A, but if there are any questions from the Zoom audience,
Please raise your hand.
and I can move you to the part of the panelists, or you can type on Zoom. Okay, Shadi is raising.
Oh, yes. Actually, there are two questions, one from Mehrdad, one from me. So Mehrdad, go ahead. Okay, so I'll go ahead. I'm wondering, it seems to me that your work could really inform the use of this technology to repair or to restore existing structures. And I wonder if you could address that in a quick way.
Yeah, absolutely. No, it's a really good point. Actually, that is one of the application area that I identified as part of the literature review that I presented in my dissertation. And there are few existing attempts to either like disassemble lumber structures using robotic manipulators. There are some that tries to detail certain existing structures and kind of like reinforce them in certain ways. It's absolutely within the realm of possibilities to extend digital fabrication, these kind of digital fabrication processes to repair or essentially work on whatever existing condition there is.
Thank you. Okay.
Congratulations, Özgür. It was wonderful. This is Merdad. We have not too much bandwidth, so we decided to share the computer. I have two questions.
Yes.
First, is it a simple yes/no answer? I believe looking at the prints, I think that the print head was always perpendicular to the surface, even when the surface was deformed. Is that correct?
It is perpendicular to the surface at every given point, except some of the areas where we had to correct it because it was actually colliding with the surface itself. But essentially, we try to keep it as normal or like perpendicular to this printed the surface that we're printing on as possible. Yes.
Yeah, great. Thank you. The second is not a question, it's just a kind of inspiration that came to my mind, which is that I noticed a significant parallel between the work that you're doing and the trajectory of automotive manufacturing. You know, if you look at today's cars, they're not seeing in the way that you're trying to see, but in the past 5 years or so, they have certainly adapted seeing technologies. They're not yet using it to inform automotive performance, but prior to that, they were sensing through the automotive suspension and steering, and they are sensing live and informing the performance of the automobile live, right? And you know, as you know, obviously, you're going over an uncharted terrain on a constant basis in a car, which is very much like the terrain that you're trying to explore. So I see a tremendous opportunity for both for your project to engage some of the existing automotive technology, but also for automotive manufacturers to tap the way that you are seeing, because they're not seeing in the way you're seeing, right?
Yeah.
They have very particular sensors in the suspension that measure particular things you're actually seeing, which is a really wild environment for automotive people to get into. So I found that really also fascinating next to everything else that you're doing.
Thank you, Merdad. It's a really good comment because funny enough, it's like computer vision essentially, especially within the last 5 to 10 years, the evolution of computer vision algorithms kind of goes hand in hand with autonomous driving and those kind of goals that are set by the industry. But yes, true. There is definitely a parallel between trying to understand the world and try to kind of tune things along the way, which as part of my future work, I hope to really look into.
Yeah, super. Thank you. Wonderful.
Congratulations.
Thank you.
Okay. I think I don't see any more raised hands or, oh wait. Check that. Okay, ready. So I don't see any more raised hands or questions. This means that it's time for the committee members to ask their questions in private. Okay. So we're gonna move to room 102, 103. But if you want to advertise these beauties that you have over here.
For anyone on Zoom, I'll speak in English and I'm speaking Turkish. I will promote everyone to be on the screen if you want to celebrate after all of the committee meeting is done. But in the meanwhile,
we're gonna celebrate.
Well, we don't know. Yes, no. I wouldn't know. I wouldn't know. Bir de Türkçe söyleyeceğim. Şimdi konferans odasına girip ufak bir toplantı yapacağız. Ama ben bu süreç içerisinde hepinizi isterseniz kameranızı açabileceğiniz şekilde panelist konumuna yükselteceğim. Eğer kalmak isterseniz seve seve, yoksa görüşmek üzere. Çok teşekkür ediyorum geldiğiniz için. Should I start recording?
You can stop recording.